Welcome all students. We are discussing the course of Data Communication and Networking, BE 7th semester Electronics and Communication Engineering. Up to now, we have discussed the basic OSI layers and its functions in our previous sessions. So today we are going to see the TCP/IP protocol suites, its comparison with OSI layer, and addressing modes or different type of addressing used in our model. So what is TCP/IP protocol suite? The TCP/IP protocol suite was developed prior to the OSI model. Therefore, layers in TCP/IP protocol suite does not exactly match to those of the OSI model. The origin of TCP/IP protocol suite was defined as having 4 layers: host-to-host networks, internet, transport, and application. However, when the TCP/IP is compared to OSI, we can say that the host-to-network layer is equivalent to the combination of physical and the data link. The internet layer is equivalent to the network layer, and the application layer is roughly doing the job of the session, presentation, and application layers, with the transport layer in the TCP/IP taking care the part of the duties in the session layer. So we assume that the TCP/IP protocol suite is made of 5 layers: physical, data link, network, transport, and application. The first 4 layers provides the physical standards: network interface, internetworking, network functions that correspond to the first 4 layers of the OSI model. The 3 topmost layer in the OSI model, however, represented in the TCP/IP by a single layer called as a application layer. We can see our discussion in this figure that it is a TCP/IP and the OSI model combined. As you can see, the yellow host to network layer is equivalent to the physical and the data link layer of OSI. The network layer is equivalent in the IP. Transport layer, it is nearly equal to the OSI layer. Now, the session, presentation, and application in the OSI model will be equivalent to the application layer of our TCP/IP protocol suite. So different protocols are there. We are going to see each and every protocol in detail in our next sessions or preceding chapters. So don't worry about the different terms: SMTP, FTP, HTTP, DNS, Telnet, UDP, TCP, RARP, ARP. Fine. So this figure is the comparison of OSI and the TCP/IP layers architecture. TCP/IP is a hierarchical protocol made up of interactive modules, each with provides a specific functionality. However, the modules are not necessarily independent, whereas the OSI specify which function belong to each its layer, and the layers of the TCP/IP protocol should contain relatively independent protocols that can be mixed and meshed depending on the needs of the system. The term hierarchical means that each upper layer protocol is supported by the one or more lower layer protocols. At the transport layer, TCP/IP defines 3 protocols. As you can see: transmission control protocol, TCP, user datagram protocol, UDP, and stream control transmission protocol, SCTP. At the network layer, the main protocol defined by the TCP/IP is IP, Internet Protocol or Internetworking Protocol. There are also some other protocols and that supports the data movement in this layer, just like ICMP, IGMP, RARP, and ARP. Yes, this figure shows the comparison of OSI and TCP/IP protocol suite in a different way. We can elaborate this. As you can see, particular layers in OSI model are written over there. The function is given and particular roles are there. TCP/IP protocol suite also there. It is a encapsulation of our data. Fine. So you can say that in the first layer of encapsulation, it is bits or data stream. Second is frame, third is packet, 4 is segment, and 5 is data. As we already seen in our OSI reference model, so there is no need to explanation this figure. So let's have some comparison between OSI and TCP/IP with help of its function, its architecture as over. So first of all, we discuss the similarities between OSI and TCP/IP model. Both have a similar architecture. Both of the models share the similar architecture. This can be illustrated by the fact that the both of them can constructed with layers. Means layer architecture is the same. Second, they can share a common application layer. Means both of the models share the common application layer. However, in the practice, this layer includes different services depending upon each model. Third comparison or third similarity. Both models have a comparable transport and network layer. This can be illustrated by the fact that whenever the functions are performed between the presentation and the network layer of OSI model, similar functions are performed in the transport layer of a TCP/IP model. Means the role of these two can be done in the transport layer of our TCP/IP protocol suite. Next, knowledge of both models is required by the networking professionals. Means knowledge must be required to implement this type of model in every system or any network, OSI or TCP/IP. So professionals should know each and every layer thoroughly. Next, both models assume that the packets are switched. Means the packet switching are there. Particular packet switching topic we are going to see preceding session. So don't worry about the packet switching. Right now you just remember this thing. The packets are forwarded as per our direction. So basically this means that the individual packets may take differing paths in order to reach the same destination. Fine. So these are the some similarities between OSI and the TCP/IP model. So what are the difference between OSI and the TCP/IP model? One of the most IMP question for your GTU and most important topic to understand both model very easily. So let us discuss the difference between OSI and the TCP/IP module. So first, OSI layer contains 7 layers, whereas in our TCP/IP it have some 4 or 5 layers. Fine. TCP/IP combines the presentation layer and the session layer into its application layer. TCP/IP appears more simpler than our OSI layer. TCP/IP combines the OSI data link layer and physical layer into the network access layer, as you can see in this figure. Data link and physical is combined by the network access layer. OSI model supports the connection oriented communication in the transport layer, whereas in the network layer it supports both connection less and connection oriented in our TCP/IP. In the TCP/IP model, it has only one mode of a transport layer but supports both modes of a transport layer, means connection and connection less and connection oriented. OSI layer and the TCP/IP models are based on the concept of the stack of the independent protocols. The function of the layers are more or less similar. 3 concept of the central OSI model: service, interface, and protocols. In the service, this defines tells what the layer does. It defines the layer's semantics. Interface, it tells the process above it how to access it. Peer protocols, protocols used in the layer are the layer's own business. TCP/IP model does not clarify the distinguish between the services, interface, and protocol. The protocols in the OSI model are better hidden than TCP/IP model and can be replaced relatively easily and as technology changes. OSI model was devised before the protocols are invented. This ordering means that the model was not based towards one particular set of protocols. Downside of the ordering is that the designer did not have much experience with the subject and did not have good idea of which functionality to put into the which layer. With the TCP/IP, the protocols came first, and then model was really being description of the existing protocol. So the protocol fit the model perfectly. So in the terms of protocols, our TCP/IP protocol suite will have advantages. But the model did not fit any other protocol stack. Fine. So our TCP/IP does not fit any other protocol stack. TCP/IP protocols are considered as to be standard around which of the internet has been developed. And the OSI model, however, is a generic and protocol independent standard. Fine. So it is some brief comparison, similarities and difference between OSI and TCP/IP protocol suite. Let's go ahead. Addressing. So what is addressing? So in general term, addressing used for some destination by which we can send our data. So 4 levels of the addresses are used in our internet employing TCP/IP protocols. First is physical address, or you can say that it is a link, our physical link. Second is our logical address, or you can say that it is IP address or internet protocol. Third is port address, or you can say that it is a process. And finally is specific addresses. So these 4 addresses we are going to see in this session. Let us start with this figure. So 4 layers are there, 4 addresses are there: physical address, logical, port and specific. We discuss each and every one with detail. So first, each address is related to the specific layer in a TCP/IP architecture as shown in our figure. The relationship of layers in TCP/IP. So our physical address will deal with underlying physical networks which is in our data link and physical layer. Our logical address or IP address can deal with a network layer and IP and other protocols. Our port address, or we can say that a particular process or application in our PC which deal with the transport layer, and specific layer will deal with the application processes. So in the physical addresses, what will you see in the physical addresses? So it is just a physical address known as a link address, and is addresses of the node as defined by its LAN or WAN. It is included in the frame used by the data link layer, which is in the lowest level addresses. The physical address have authority to have the networks over the LAN or WAN. The size and the format of this address vary depending on the network. For example, the internet uses the 6-byte or 48-bit physical address and is impaired on the network interface card called as a NIC. So it is a unique address given to your node. The node will be PC, laptop, mobile, anything. It is our Ethernet, or you can physical address which is uniquely in our world. Fine. As you can see, some application will run only on one device. Why they run only one device? They just mask their application with our physical address or MAC ID. Let's have an example. In the given figure, it shows the physical addressing concept. Over there, our sender have a 10 physical address, will send some data to the receiver which have its physical address 87. So it will generate a particular frame over in the frame, in the header section, first is a destination address. We are sending our data to the 87, so 87 is there. Then it's our source address, just like our 10 physical address. Then our data and a trailer for our error checking or correction. So it forwarded through our LAN. This LAN will forward the frame to all the PCs which are connected. So a PC which have a physical address 28 does not accept the frame. Why? Because the matching between destination address and its own address will not same. So it just forward ahead and packet is dropped. Same thing will be occur at 53 node. When our packet will arrive at the receiver which have a 87 physical address, our destination address match with our receiver, the packet is accepted and the data is given to the receiver. So it is a physical address figure. Fine. We have shown a bus topology for an isolated LAN. In the bus topology, the frame is propagated in the both direction, left or right. The frame is propagated into the left dice when it reaches to the end of the cable, if the cable is end is terminated approximately. The frame propagates into the right, sent to the every station of the network. If each station will have a physical address other than 87, drop the frame because the destination is does not same its own physical address. The intended destination computer, however, finds the match between the destination address in the frame but its own physical address. The frame is checked, the header and the trailer is dropped, and the data is decapsulated and delivered to the upper layer. Fine. Let's take another example. Most local area networks uses 48-bit 6-byte physical address written in the 12 hexadecimal digit. Every byte 2 hexadecimal digits is separated by the colon as shown in our figure. So it is a structure of our hexadecimal digits or physical address. You can find your physical address with the help of the command prompt in Windows, and you can find your physical address through the terminal for the Linux. There are specific commands to define or to find our physical address. Fine. Next is logical address. So what is a logical address? As we can see, it is a IP address. We can say that the logical address are necessary for a universal communication that are independent of underlying physical networks. The physical address are not adequate in the inter-network environment where the different networks can be have different address formats. The universal addressing system needed in which each host can be identified uniquely, means uniquely identification is required regardless of its underlying physical network. So for the universal communication, a uniquely identified addressing must be required, just like our IP address. The logical addresses are designed for this purpose. The logic address in the internet is currently 32 bits. Address can be uniquely defined the host connected to the internet. Right now, the capacity of the logic address will be 2 raised to 32, will be achieved within a few years or within a decade. Then IP version 6 contains 128-bit address, means 2 raised to 128 will be used after the 32-bit address occupied. No two publicly addressed and visible hosts can and the internet have a same IP address. So it's maybe you face in our LAN lab that if you enter the some IP address, then it will also show that it is IP conflict, means the same IP will be taken by the another PC. So you enter the different IP address to connect your PC to the LAN. Let's have an example. Over here, figure shows the part of the internet with the two routers connected 3 lanes. It is a router and it is 3 lanes. These 2 routers connected with the 3 lanes. Each device, computer or the router, has a pair of address, logical and physical, for each connection. In this case, each computer is connected to only one link and therefore has only one pair of address. Each router, however, is connected to the 3 networks. Only 2 are shown in the figure. So each router has a 3 pairs of address, one for the each connection. Although it may be obvious that each router must have a separate physical address for the each connection, it may be not obvious that why it is need a logical address for the each connection. We will discuss in the routing chapter. Fine. Right now you just understand the figure. The computer with the logic address A and the physical address 10, A/10, needs to send a packet to the computer with the logic address P and its physical address 95. We use the letters to show the logical address and the number of physical address, but note that both are actually numbers, as we see in the later in the chapter. The sender encapsulates the data in the packet at the network layer and adds the 2 logical address A and P. Note that the most protocols, the logical sources address comes before the logic destination address, contrary to the order of the physical address. The network layer, however, needs to find the physical address of the next hop before the packets can be delivered. The network layer consists of its routing table and finds the logic address to the next hop, router 1, to the F. The ARP, which is used by our layer address resolution protocol, will find the physical address of the router 1 and that corresponds to the logic address 20. Now the network layer passes this address to the data link layer, which will then encapsulates the packet in the physical destination address 20 and the physical source address 10. The frame is received by every device in the LAN 1, but it is discarded by all the expect router 1, which finds that the destination physical address in the frame matches with its own physical address. The router recapitulates the packet from the frame to read the logical address or the destination address P. Since the logical destination address does not match the router's logical address, the router knows that the packet needs to be forwarded. So packet does not lost. The router consists its routing table and ARP to find the physical destination address of the next hop, or the router 2 creates the new frame and encapsulates the packet and send it to the router 2. Note, the physical address in the frame. What is the physical in the frame? Yes. The source physical address changes to 10 to 99. Or you can see. Fine. The destination physical address changes from 10 to 33. Very good. 10 to 33. The 20 to 33 means the router 1 physical address is 20, router 2 physical address is 33. The logical source and the destination address must remain same. Otherwise the packet will be lost, means our AP will be same. It is our physical address, it is our logical address. So our logical address will be remain same up to the destination. Our physical address will be changed according to our devices or our physical connection. At the router 2, we have similar scenario. The physical address are changed and the new frame is sent to the destination computer. When the frame reaches the destination, the packet is decapsulated. The destination logic address P matches with the logical address of the computer. As you can see, P and P. The data are decapsulated from the packets and delivered to the upper layer. Note that although the physical layer will change from hop to hop, the logical address will remain same for the source to the destination address. There are some expectation to this rule will be discovered later in this course. So we can conclude that the physical address will change from hop to hop or node to node, but the logical address will usually remain same. Port address. What is port address? The IP address and the physical address are necessary for the quality of the data to travel from a source to the destination host. However, the arrival at destination host is not the final object of the data communication of the internet. The system that sends the nothing but the data from one computer to another is not a complete. Today, computer are devices that can run multiple processes at the same time. Each end objective of the internet communication is a process communication with one another. For example, computer A can communicate with computer C using the telnet. At the same time, computer A communicate with the computer B using the file transfer protocol. For this process to receive the data simultaneously, we need a method to label the different processes. In other words, they need an addresses. In the TCP/IP architecture, the label assigned to a process is called the port address, and the port address in the TCP/IP have a length of 16 bits. Fine. As I already told you, it is the label assigned to the each process for process to process communication. Let's have an example. In this figure, the port addressing are used. A process in the sender A called label as A will try to connect with the process at the receiver P at the level of the J. So in this figure, it shows the two computer connecting via the internet. The sending computer is running three processes A, B and C with the port address ABC. The receiving computer is running the two processes at the time with the process have a port address of J and K. The process A is sending a computer needs to communicate with the process J in the receiving computer. Note that although the both computers are using the same application FTP, file transfer protocol for example, the port address are different because one is a client program and another is a server program. To show that the data from process A needs to be delivered to the process J, not the K, the transport layer encapsulates the data from the application layer in the packets and adds two ports address A and J. Fine. So you can see that A and J, the source and the destination. The packets from the transport layer is then encapsulates it to the another packet at the network layer with the logical source and the destination A and P at the network layer. So it is our logic address. Finally, this packet is encapsulated in the frame with the physical source and the destination address to the next hop. We have not shown the physical address because they change from hop to hop inside the cloud designated as the internet. Note that although the physical address changes from hop to hop, the logical and the port address remains same from the source to the destination. There are some exceptions to this rule we will discuss in the later of this course. Fine. So you can say that the process A can communicate with the process J with this port address architecture. Let's have an example. The port address is 16-bit address represented by the one decimal number as shown is 753. A 16-bit port address represented as a one single number. We can conclude that the physical address changes from hop to hop, but the logical and the port address usually remain same. Fine. So you can see this, our logical address, our port address, and over here the physical address, it will change. So this will be remain same in entire communication. Final, the specific addresses. Some applications have a user-friendly addresses that are designed for the specific addresses. Example, we can include our email address just as student@SSIT.co.in, or the URL. You can say that universal resource locator. For example, our institute website www.ssit.co.in. So this is called as a special or specific address. The first defines the reception of the email, and the second is used to find the document in the World Wide Web. These addresses, however, get changed to the corresponding port and logical address by sending computer. So, in this discussion, we have discussed the TCP/IP models in detail. We have compared the TCP/IP and OSI model with its similarities and difference between them. And lastly, we have discussed the addressing of each and every layers, or we can say that the addressing in the TCP/IP. So this is a question for you. Write down in your notebook and send back it to me as per the given direction. Thank you, student. See you in the next session.